Welcome to PEP 8, a not quite as simple computer. We'll start with some credits. PEP 8 is the brainchild of J. Stanley Warford, professor of computer science at Pepperdine University, and is used along with his textbook for both undergraduate and graduate level courses there. So it's actually pretty close to a real computer, a small one, but a real one. The reason I say small is its memory is limited to 64K, or 2 to the 16th. Still a lot better than the super simple computer, where we had a whopping 16 words of memory. Notice how that PEP 8's memory, like almost all modern computers, is organized in bytes, not in the 16-bit words we used with SSC. In its CPU, it has the same kind of registers that SSC does. It has a program counter. It's 16 bits worth of program counter, and now all the 16 bits are useful to address those 64K bytes of memory. It has a 16-bit accumulator, just like SSC, and again, all those 16 bits are useful now. Its instruction register is quite a bit more complicated, however. Instead of just 16 bits representing each individual 2-byte instruction from SSC, we now have two options. We have an instruction specifier and an optional operand specifier. So an instruction in PEP 8 land can be either 8 bits, 1 byte, or 24 bits, 3 bytes. More on that later. Remember, the temp register in SSC was used to load an operand as needed from memory or from an instruction, and the same happens here in PEP 8. You can see that fetch of an operand from memory, and it'll show up in that operand location in the CPU. Now, PEP 8 has a couple things that SSC didn't have. First, and some things that we'll use, are the status bits, N, Z, V, and C. They're 1 bit each, and we'll talk about those a little bit later. It also has two additional registers, one called an index register, and the other called a stack pointer. We'll talk briefly about these, but not get into gory detail. So let's look at instructions now. Recall that in SSC, each 16-bit instruction had a 4-bit opcode, followed by a 12-bit operand specifier. In PEP 8, the opcode has grown and become a little more complicated. In fact, we now have 8 bits of what we call an instruction specifier, and then a full 16 bits of operand specifier for some instructions. Some don't require it. Looking at the PEP 8 instruction specifier a little more carefully, we'll see that it's divided into several pieces. The first 4 bits are an opcode, just like we had back in SSC. The last 3 bits are very interesting. They specify the addressing mode. So far, we've seen 2 addressing modes in SSC, immediate and direct. Those are represented by the bit pattern 000 and 001 in the addressing mode portion of the instruction specifier. As you can probably guess, there are 6 other addressing modes. We'll touch on some of them, but some of them get pretty complicated. Finally, that bit in the middle is used usually to specify a register that the opcode works with. We'll be mostly using the accumulator, so it will mostly be 0 for us, but you can also operate on the index register directly, and a few opcodes actually use that as a 5th bit for the opcode, and we'll see some of those. So let's compare some specific instructions. Here's the simple stop instruction, and you can see the only difference really is the opcode. Now, if we do a load immediate, that is, take the number 10 directly from the instruction and put it in the accumulator, again, you'll see a difference in the opcode, and notice that the PEP 8 instruction specifier bits that correspond to the addressing mode are all set to 0. And this will, in both cases, load the constant 10 into the accumulator. Now, if instead we're loading from a memory location, the SSC changes its whole opcode. PEP 8 just changes the bit in the addressing mode, and the opcode actually stays the same. Here's an example of an add operation. Again, notice that the opcodes differ, and because we're adding from memory, PEP8 has the addressing mode set to 1. And here's the power of having that separated address mode. PEP8 can also do an add immediate without going to memory. SSC didn't have an opcode for that, and so it couldn't do it. Input-output is also much more powerful in PEP8 than in SSC. It uses a keyboard-style input, which means we can type in both numbers and ASCII characters. There's also a way that you can set it up in what's called batch or pre-recorded mode, which is really handy if you're trying to test a program with some extensive input. It saves you from typing it every time. Now this obviously implies some differences in the input-output instructions. In SSC, to get number input to the accumulator, we used a particular opcode. In PEP8, we also use an opcode. Notice this is one of those 5-bit special opcodes. It's actually an instruction trap if you really want to get into the graduate level course. And instead of going to the accumulator, it goes to memory. Number output, similarly, is a 5-bit opcode, and notice that this can be either immediate or direct in PEP7. So, in the case shown here, we can take it as immediate with an addressing mode of 0, but if we simply change the addressing mode to 1, we can output directly from memory. So let's summarize the differences between SSC and PEP8. First of all, we have 2 to the 16th bytes of memory, 64 kilobytes. Second, we have 32 opcodes, or sort of. As we pointed out, a lot of those are 4-bit opcodes with a separate register bit. We have variable-sized instructions, 1 or 3 bytes, depending on what we need. Most opcodes can be immediate or direct in addressing mode. Addressing mode is separated from the opcode as to being sort of bundled with it in those 11 we had with SSC. Input and output is directly to memory rather than to the accumulator. And finally, we have a more sophisticated human interface device, typewriter-style input and output, rather than typing numbers only. Putting it all together, here's what PEP8 looks like in its simulated running. The next podcast goes into more detail about how to operate the simulator, or you could fire it up and explore yourself. Good luck!